you're probably a little bit curious about how we experience color. So the thing is that color is not an inherent part of an object. So for example, I wore some red shoes today. That redness is not technically inherent in the object itself. Colors are based off of the wavelengths that are reflected. Now, one of the things that's really nice about things like clothing and paint is that we know this and we can basically make things different colors, but ultimately our experience of color is based on reflected wavelengths. So the question becomes, why do colors tend to stay the same even when lighting conditions change? So I mentioned that dark blue dusky hour when colors are hard to see. But that doesn't mean that if it's after dark, I go out and look for my white car and I go, the light has changed. I cannot find my car because that does not look like the same shade of white to me. And the reason that we don't do that is because we do something that's white in the dark still looks white. So it just doesn't quite have the same intensity. So one of the things that we've discovered is that color does not solely depend on the wavelengths that are reflected from the object. If that were true, colors would look different and we perceive colors as being different in the dark versus in the light. So what we have to kind of help with this is something that's occasionally referred to as redneck theory. We have an overall ratio of the wavelengths that are reflected by the object and nearby adjacent surfaces. So what we do is we take into account the lighting source, we take into account other nearby surfaces, and that ratio will be constant no matter what, regardless of whether lighting conditions are good or they're poor. Now, one thing that you might not know is that colors are not typically things that we see in isolation. Most of the time, our experience of a color is going to be with multiple colors that are presented. And so one of the things that's kind of interesting is that our experience of a color is actually influenced by other colors being around it. So what you're looking at in this case is an example of color contrast. So if you'll notice, if you look at this bar, the bar looks greener when it's up against red, and it looks redder when it's up against green, even though it's the same color regardless. This is color contrast. So what will happen is that when we look at a red background, we're going to see green in a neighboring region because that's the opponent color. When we're looking at green, things will take on more of a reddish appearance. Now, color contrast and playing with light and shadow can be a lot of fun. So I'm going to go ahead and pull this up in slideshow format so you can really appreciate this. So this is an illusion that I saw back when I was in college, and it still blows my mind to this day. So because of the principles of color contrast, you may perceive that A and B are different colors. But research has actually found, especially if you take these gray stripes, A and B are exactly the same color. The reason that we don't see and perceive B as being the same color as A is because this cylinder casts a shadow. And so even though this B is the same color as A, we perceive it as being lighter because we discount the fact there's a shadow there. So we go, oh, there's a shadow here. So this darkness must actually mean that this is a lighter color. And you can actually play around with this. There are programs and apps and things like that that will let you actually cut out B and move it around, and it will actually show you that it is identical to A. The only reason that you don't think it is because that shadow is getting in the way. One of the other things that we know is that colors can really bleed into each other. So here's that color contrast. So here, the red looks a little bit more red than it does here. Here, the green looks a little greener than it does in this one. The same with blue and yellow. The other thing that we can find is color assimilation. Colors that are neighboring to each other will take on the chromatic quality. So here's the same shade of blue in both of these squares, but because this is surrounded by red, it looks like a more deep blue. Here, it looks like a greener blue. here's a more orange yellow, here's a more green yellow, and so on and so forth. Here's a cooler red, here's a warmer red. Here's a warmer green, here's a cooler green. Now, one of the ways that you can actually see this in action is with these spirals. Now, odds are pretty good that these spirals look like shades of both blue and green. This is because of color assimilation, though. If you look very closely, these colors, especially at the edges of the figure, the colors are the exact same shade. But this particular spiral that I'm scrolling my cursor through is intercut with orange, so it has a bit of a warmer quality. This spiral is intercut with pink, and so it has a bit of a cooler quality, thus creating the blue and green spirals that are actually the same color. Now, things like color contrast lead to some really interesting cases, like the case of the dress. And this was really popular back in 2015 because it was probably one of the first times where people were looking at the exact same object and they were seeing completely different things. Now, sitting under the blue light of my computer, right now the dress looks gold and to a lesser extent, a dusky blue. Some of you might see white and gold. Some of you might see the actual color that it is, black and blue. And now that I've actually said black and blue and I know it's black and blue, my brain is actually trying to get it to switch. So I want to briefly show you why things like this happen and why the dress works the way it does. So I'm going to go ahead and open this link. It will be fun, but I'll keep it pretty quick for you. The dress that broke the internet. This happened the night before I was teaching a biopsych class. By the time I got to biopsych the next day, half of the students were saying, tell us about the dress, and the other half were telling me, please don't talk about the dress. So research surveyed thousands of people, many who had never seen a picture of the garment. 57% described it as black and blue, 30% said it was white and gold, 11% said it was blue and brown. I don't know who this 2% is that saw other colors, but here's why. There are a variety of different reasons why people kind of saw these differently. People who saw white and gold probably spend more time exposed to natural daylight. Viewers who spend more time surrounded by artificial light, which is blue in nature, probably saw the dresses black and blue. One framework for understanding why you get these variations is to consider how light is contaminated by outside illumination, such as a blue sky or incandescent light. Your visual system has to decide whether it gets rid of the shorter, bluer wavelengths of light or the longer, redder wavelengths, and that may change how you see the dress. So there are a variety of different ways to see it, and I think the light idea is very reasonable. I had several experiences based on the scenario I was in, whether I was in the basement of Hink House or outside in the sun, and I would see the dress differently. So if you see the dress as white and gold, it doesn't mean that you're weird or anything like that. Color, we have categories, and the categories aren't necessarily sharp, but we define them as sharp. So when we get something that's in between or ambiguous like this dress is, we really seek to categorize it. And so we lead to these either or distinctions. Now let's talk about depth perception. Your depth perception is incredibly amazing. And I want you to think about this. Your retina is basically a flat sheet against your eyeball. And whenever you are looking at something out in the three-dimensional world, it then goes into your retina where it becomes a 2D image, and then you take that 2D image and you turn it back into a three-dimensional perception of the world. So in one sense, you're actually moving from Euclidean geometry, where all of the angles of a triangle add up to 180 degrees, to a non-Euclidean, as you can see here, where the angles of a triangle could actually be more than 180, and take that weirdness and you reconvert it into an appropriate representation of the world. And it turns out that we have a lot of different cues that can help us. So monocular cues are those depth cues. And by the way, depth cues are really important. They help us indicate distance. They also help us from keep us from walking into things, which is really important. But we use a combination of depth cues to help us. And the first ones we're going to talk about are monocular cues. They use a single eye. This includes things like linear perspective, texture gradient, shading, interposition, and familiar size. So here's what linear perspective is. The idea is that the world is basically constructed as a series of parallel lines, such as you see here in this image. The more closely the lines look like they're converging, the farther away you can assume something is. Here's another case. This is utilizing texture gradient. So the bigger bunnies are perceived to be up close. The tinier bunnies are perceived to be farther away. Now, in the case of our bigger bunnies, what you'll notice is that you can probably see more of their fur, you can see their whiskers, you see a lot more texture. The tinier bunnies in the back, you probably don't get those fine details. So the closer that you are to something, the more fine details and texture you can see. The farther something is away from you, the less textured it appears. We can use shading to help give us a sense of depth. So as you can see, shading here kind of changes our perception and depth of an object. Whenever you wear makeup, you are utilizing the principles of shaping to create these bigger eyes, smaller eyes, or a more contoured or angular face. Interposition. This is generally the idea that objects that are closer to us block objects that are farther away from us. So here, this circle is not being blocked by anything, so we assume that it's closer. It is blocking the square, so we assume that the circle is closer to us than the square. And then finally, the square is blocking the triangle, and we're going to assume that because of the way that these shapes are organized, that the triangle must be the furthest away from us. Familiar size. Generally, we know the size of objects. So if something appears larger to us, we're going to assume that it's closer to us because generally objects that we're very familiar with don't just suddenly shrink and grow for no reason. So you can see kind of in this image, as the woman brings her hand closer, her hand didn't suddenly grow. We know that the size of hands tends to be pretty fixed. So if our hand's getting larger, it must be closer to us. If our hand is farther away, we know that or if our hand looks smaller, we can assume that it's farther away. So those are all monocular cues. You only need one eye to be able to use them. Binocular cues are different. Binocular cues use both eyes. So one of the things that we find is that because your eyes occupy slightly different positions in your head, each of them gets a slightly different view of the world. You can actually do this right now. Keep one eye open, close the other eye, and then just shift from opening and closing your eyes back and forth, back and forth, back and forth. Things might look like they move slightly, and that's because each eye is getting a slightly different view. They're slightly different. And because they're slightly different, we can actually use these differences to calculate depth. And this is what's known as stereopsis. Stereopsis can actually be mimicked in these magic eye images. So anytime that you go to a 3D movie or if you look at a magic eye photo like this one, what's happening is that they're basically exaggerating this stereopsis to create a sense of distance and depth. And you can see a 3D image where one may not necessarily exist. We have binocular cues, monocular cues, and then finally oculomotor cues. These use eye movements. Generally, objects that are closer, our eyes will move inward in a process that's known as vergence. It's convergence if you're moving in, it's divergence if you're moving out. Additionally, we can do accommodation, and the lens can thicken to focus on close objects. That's all for now. I will have more for you in the next couple of days. Bye.